Welcome to the Attochem second annual workshop of the so it's the second one that it's held virtually, unfortunately, due to the pandemic situation we had and we're still currently experiencing partially. But both me and Fernando, of course, are happy to be here and to see so many participants to the workshop, although again held in a virtual format. So I would like to share a few slides. Okay. Perfect. So, as I said, the second annual workshop this year is held by DAISY, and we put together quite an intense program, but this time we mostly decided to concentrate, as you have seen, the talks in the morning. Then we will have a long break for the lunch break, and then poster sessions for both today and tomorrow. And you can find all the details of our program, as you know, in the website here. So I would like to thank, first of all, the local organizing committee, which together with me has put together this program. So Eric Manson, Vincent Beni, and Andrea Trapattoni. And of course, the core group of the action who proposed the many speakers, and all the speakers who accepted our invitation to the workshop. I want to point out a few rules. So as you see, we have about 30 minutes for the talks, so 25 minutes of talk and 5 minutes of questions. But then we have half an hour of discussion. So we have organized a breakout room, one per speaker, where you can ask detailed questions to the speakers. On a Friday, we will also have the closing remarks together with the poster awards session. So let me spend just a couple of words about DAISY. I want to spend only a few minutes on that. So unfortunately, you're not here, so you cannot visit the campus. You can only see here a picture of this is my vision of the campus. DAISY has 2,600 employees from 77 countries. About 3,000 guest researchers per year are coming to DAISY from more than 30 countries. There are about 300 buildings on campus, so it's a huge campus, and we have about 10,000 visitors coming for public tours at DAISY every year. The peculiarity of DAISY is that we have many light facilities, so maybe here I can go a little bit more into the details what concerns the photon science facilities. We have a bright synchrotron, Petra 3, which is providing X-ray light, and it will be upgraded soon in Petra 4 to be one of the, as I said, brightest sources in the so synchrotrons in the X-rays. Then we have FLASH, which is SOFTX free electron laser operating in this photon energy range with durations in the femtosecond range, and also will be upgraded with a program which is called FLASH 2020 Plus to be an external seeded free electron laser with tunable ondulators and still operate in the SOFTX spectral range at high repetition rate. On campus, we also have the European XFEL, which is an X-ray free electron laser, and it's also operating in the femtosecond domain with a program to go to the Few-Femtosecond, only the Sub-Femtosecond scale, approaching the topics of our network. We have research centers, including the Center for Free Electron Laser Science, the Center for X-ray and Nanoscience, the Center for Structural System Biology, and the Center for Molecular Water Science on campus, working on these different topics and exploiting these advanced laser and light sources. At the Center for Free Electron Laser Science in particular, We have several partner institutions, including beyond DAISY, the University of Hamburg and the Max Planck Institute for Structure and Dynamics of Matter. And here we developed advanced light sources, including tabletop, attosecond sources for the investigation of ultra-short timescales. And here we combine both theoretical and experimental studies to the matter. So here you can find some details about us. So this was just an overview on the hosting institution. Again, I want to go back to the program because we just wanted to provide a very short introduction. And I want to recall again that in the last day, we will have a dedicated session for awarding, for giving 3 poster prizes at 2:30. So I invite all the participants to be there because we will, basically invite the awardees to the stage to receive their grant, and these have been kindly sponsored by Coherent. Okay, this was everything I wanted to say. I want to give the word to Fernando to give us a few numbers, or so to say, statistics about the Attochem action, and also to welcome all of you. So thank you, Fernando. Please, I stop sharing my screen.
Thank you, Francesca. Good morning, everybody. I want to thank very much Francesca and her team for the organization of this meeting, which, as she said, unfortunately has to be online once again. Let's hope next year this will be in person. So I will take just a few minutes just to introduce the Attochem network to those who do not know about it. So I will share my screen. So what's going on with this? Okay, good. I hope you can see now my my presentation here. Okay, so basically the Attochem network is organized around 3 working groups. One is devoted mainly to experimental developments. It's coordinated by Caterina Bozzi. It's new Attosecond techniques for the control of electron dynamics and molecules. There is a second working group devoted mainly to theoretical advances and computational developments. And this is coordinated by Ladislau Nagy. And finally, there is a third working group coordinated by Frank Lepine about how to use these tools to image Attosecond charge migration and chemical reactivity. The activities that are organized under the umbrella of Attochem are very diverse. One of them is this general meeting that we are having right now. That's why you are here. But we also organize reduced working group meetings, reduced in number of participants to discuss specific topics. There are also meetings organized by young scientists in the network and training schools for PhD students and young postdocs. And we also organize a webinar series. Well, this is already in place, and we hope that this will go on in the near future. One of the most interesting instruments that unfortunately could not be used so much until now is the short-term scientific missions, which are, visits to laboratories involved in the network that are covered by our action and that are very, very useful to establish or develop existing collaborations. And there are also grants to attend conferences from countries belonging mainly to Eastern Europe. And now we have also virtual mobility grants to organize online activities that are very important nowadays because of this pandemic that hopefully is going to an end. Here you see a few email addresses where you can contact the working group coordinators and just to get also general information. So apart from the working group coordinators, Francesca is not only organizing this meeting, but is the vice chair of the action. And for the STSMs, Bernard Pirot is the coordinator. He's the one who manages all the applications that are received. And we also have Agnes Bibok as a coordinator of the ITC grants. For the gender balances, Violeta Petrovic, and for the organization of events concerning young scientists, Iva Vrezinova. And a very important person nowadays during this pandemic is Aurora Ponce, who is taking care of all the organization of the virtual events, many virtual events, and also dissemination activities. And we are very thankful to our external advisory board, in which we count with the help of Luca Argenti, Ludi Mauro, Kiyoshi Ueda, Monica Garcia, and Thomas Metzer. So that's the end. Just to show you the present numbers. Well, so far there are 26 countries participating in this network, and we have 30% of them come from Eastern Europe mainly, and well, I think it's a very lively network in spite of the difficulties we are having nowadays, and we hope that next year everything will be more or less normal and we can meet in person. So remember the activities we organize. I encourage all of you to contact us if you are interested in participating, and if you are interested in using our tools and to get funding for them, please don't hesitate to contact us and tell us. That's all from my side. Thank you very much for being there, and I hope you will have a very, very interesting and successful meeting.
Thank you very much, Fernando, for the very nice introduction about the Attochem network. So we are now perfectly in time to start with the first session of the workshop. So the first session is entitled Attosecond Photoionization Dynamics in Atoms and Molecules. I will be chairing the session. So we already have the first speaker on the stage, Anne Roulier. Welcome, Anne. So Anne will be talking about phase measurements by attosecond interferometry. We will have, as I said, about 25 minutes talk, and then please leave a few minutes for urgent questions from the audience. The audience can post the questions in the live Q&A. And then we will have a dedicated discussion session at the end, as I was mentioning. So please, Anne, the stage is yours.
Thank you. Can you see my screen?
Yes, it's working.
Okay, thank you very much for your invitation. It's a pleasure to open this meeting. So this talk is going to be about phase measurements by attosecond interferometry. And what I'm going to discuss is and to use in this talk is the process of laser-assisted photoionization, which has been used in our field since many, many years. In this process, one ionizes atoms or molecules using XUV radiation and a tracing field at a variable time delay, and one detects the photoelectrons. This process has been used in the first place to actually characterize the high-order harmonics in the 1990s. Then, of course, it has been used in 2001 and later to show that we had attosecond pulses in a train of pulses, and also to characterize these attosecond pulses. Lately, it has been used very successfully to characterize photoionization time delays in atoms and molecules, and then this has been extended to angular resolution. In parallel, it has been used to characterize resonant photoionization. And it is now applied to a variety of systems, not only atoms, but molecules, and also not only in gas phase, but in liquid and solid phase. So in these talks, I want to tell you about recent development we have done in Lund. The first one will be about the characterization of single photon ionization, and including the angular resolution in the case of multiple angular channels. And the first one is try to improve. The second one is to really improve the spectral resolution in these measurements and look at resonant photoionization. So I start by a brief introduction to this technique in the case where the XUV radiation is a comb of high-order harmonics, or in the time domain attosecond pulse train. And it's then an interferometric technique, also called rabbit technique, and the information is obtained by looking at how the sidebands, which are created by absorption of XUV radiation plus infrared plus this tracing field, or emission of one photon from this tracing field. Here we have a quantum interferometer, and the information is obtained by looking at the intensity of these sidebands as a function of the delay between the XUV radiation, here this comb of high-order harmonics, and the infrared radiation. Now, one obtain interference equation here, and again the information that we are looking for is included in this phase offset, and this phase offset is related to the spectral derivative of the attosecond electron wave packet that is created in this process, in this two-photon process. And this spectral derivative can be shown to include three contributions. One is, of course, the contribution from the XUV source, from the excitation pulse. One is coming from the interaction with the infrared field, with the tracing field, and it involves continuum transition. We can call this term for induced by the measurements, since it is necessary to have this interaction in order to measure the interferences. And finally, you have a third term, which is related to one photon ionization by the XUV radiation. And in the case of one angular channel, this is the Wigner delay, and is related to the derivative of the scattering phase of the one photon ionization process. So this has led to a series of I think very important measurements, the measurement of these time delays. However, this is strictly valid in the case where you have one angular channel, or maybe one dominant angular channel. And one question is, can we extend this rabbit technique, this interferometric technique, to a more complicated case where you have several channels contributing to the ionization process? So let's consider, for example, the case of neon, close to the ionization threshold of the 2p shell. So we are really talking here about energies between 20 and 50 eV. And in this case, we are in the situation where you can ionize the 2p shell to the S or to the D continua with similar probabilities. So one of the questions is, can we retrieve the phase and amplitude of this two angular channel? Can we extend this rabbit technique to really characterize the two angular channel, which is a really complete characterization of the photoionization process? And to perform complete experiments has been really a holy grail in the synchrotron radiation community. So can we help with our Attosecond technique to retrieve these different angular channels? So let's look in more detail to the photoionization of neon in the 2p shell. As you can see on this diagram, you have several channels. You go to S and D by one photoionization, and then P and F by absorption of the second photon. This is for m equals 0. In addition, there is an incoherent sum of the contribution of m equals 0 and initial state and m equal plus or minus 1, where you, of course, you cannot go to the S channel when you start from m equal plus or minus 1. So it's complicated. So the experiment that I'm going to tell you about has been performed at the experimental setup in Lund, which we call intense XUV beamline, which is driven by Per and Johnson. And what I'm telling you is really one of the important results of Jasper Pescher's thesis, which will be defended on Friday. So this setup is designed to really optimize the energy, the output energy of the high harmonics or of the attosecond pulses. So it is a very long setup with a footprint of about 20 meters. It uses this scaling of high order harmonic generation with loose focusing in order to produce a lot of energy per pulse. It uses the 40 terawatt laser system of in Lund, loose focusing geometry. The interferometer, which is used to separate the pump and the probe field, the XUV radiation and the tracing field, is a rather compact interferometer, which is after the generation, and it has this diamond shape using two Hole mirrors. And the infrared radiation, which is used for the generation, is filtered out using silica plate and an aluminum filter. And now both beams are refocused into an application chamber using two toroidal mirrors in a Voltaire optics configuration. And the electrons are detected using a velocity map imaging spectrometer. This results show you first the angular integrated rabbit spectrogram, showing you as usual the harmonics and the oscillating sidebands. And then the results on the right show you the delay integrated photoelectron angular distribution with different photoelectron angular distribution for the electrons created by absorption of the harmonics or those leading to the sideband peaks, which are combination of P and F waves, and here we have S and D waves. Now the information is of course included in this angle and delay dependence of the sidebands, as you can see here for sideband 16, showing you this how the signal depends both on the delay and on the emission angle. So the procedure consists in analyzing this photo angular distribution by looking for the coefficient of an expansion in Legendre polynomials up to order 4, since it's a 2-photon process. So one retrieves these coefficients H0, H2, and H4, and then study this coefficient as a function of delay. And these coefficients oscillates very nicely with delay, which means that they can be described by 3 coefficients: the amplitude of the oscillation, the mean of the oscillation, and the phase of the oscillation. So we characterize our experimental result by 3 coefficients for each HI. So in total, we have 9 parameters, independent parameters that we can extract from the experiment. So now the next question is are these 9 parameters enough to retrieve what we are looking for, and especially this 1 photon phase for the different angular channels that we would like to determine. So this expression here shows how this sideband intensity looks like, and it's quite complicated expression. You have to sum coherently the different angular channels, and you are summing both an absorption process and an emission process, emission of course the dressing field. And then you have to sum incoherently over initial states, over the M states. And these M quantities here are 2 photon transitions, and this can be written with angular coefficients, which you know, 2 photon amplitudes, which you don't know, and then a phase factor, which includes again the CC phase, 1 photon phase, and then a phase due to the XUV radiation. So obviously there are a little bit too many unknown quantities in this expression to proceed. So the idea was to actually use what we know about these CC transitions. So and we can calculate the CC transition, and this continuum transition are very much universal. As you can see on this plot, this represents calculation, 2 photon calculation by Eva Lindroth and Jimmy Winblad from Stockholm University on different atomic system and different initial states. And what you can see on this plot is that this the phase of the continuum transition is pretty much universal. It depends whether you increase a little bit, whether you increase or decrease angular momentum in the transition. This is the difference between these 2 plots, tiny difference. And of course, it depends on whether you do a 2 photon absorption or 1 photon absorption plus 1 photon emission. This is the difference between the up and down plots. But apart from that, it's very much universal quantity. So we use these phases in our phase retrieval. There is also the amplitude of this continuum transition is also pretty much universal. The ratio of the amplitude of going up in angular momentum and going down in angular momentum is quite universal, as you can see on these plots. So we use also this result to reduce the number of unknown quantities. And when we do that, we realize that now in this term there are not only 9 unknown quantities that you can retrieve using the 9 experimental parameters in the experiment. So this is what we have done, and this is the results. So this is the retrieval of the 1 photon phase for the 2 angular channels going to the S wave or to the D wave in blue. So the points are the retrieved experimental phases for the 2 channels, and the lines are theoretical calculations. I would like to stress that in this retrieval, there is only 1 arbitrary phase that you cannot retrieve, for example, this one, and then all of them are retrieved from the first assumption. So what you can see in this plot, then we can try to interpret this phase variation using the expression that you see on the right, phase, the scattering phase. The phase that is measured, the one photon phase, is the sum of a Coulomb phase, a phase due to the short range potential, and then a contribution from the centrifugal potential. The Coulomb phase are indicated by this dashed line. You can calculate them quite easily. The contribution of the short range potential affects only the S wave, which penetrates close to the core. And using calculation from Kennedy and Manson, this contribution is about 1.2 pi. And then the centrifugal potential phase is only for the D wave, leads to this pi phase jump. And doing this, we get this dashed line, which reproduce very well both the calculation and the experimental results. And we can also, of course, retrieve the amplitude of the two angular channels simply by doing one photoionization and retrieve the from the photo angular distribution, retrieve, for example, here the ratio between the two amplitudes. So this was the first experiment I wanted to tell you about. I would like to say a brief word about recent development in resonant photoionization, where we try to really push the resolution of our technique, the spectral resolution of our technique. So instead of looking at fast dynamics, as I just mentioned, non-resonant photoionization, now we look at the influence of a discrete state, for example, an autoionization resonance, using the same technique, this interferometric technique, to read the phase of the electron wave packet. And this is longer dynamics in the femtosecond range, and this has been pioneered by many groups. For example, the group of Pascal Salières and of Ursula Keller. So the experimental setup which is used in that experiment is maybe more conventional attosecond setup with an interferometer, which is shown here. And in that particular experiment, we really try to improve the spectral resolution by using rather narrow bandwidths for the harmonics, and also especially we have an interferometric filter in the probe field, which really is very useful to improve the spectral resolution. The spectral resolution of our experiments is then mainly determined by the spectrometer, and we can also use the convolution algorithm to further improve the resolution. This is a collaboration with the group of Raymond Feldfeld at Gothenburg University, and I would like to stress that these results are really those of David Busto. Okay, so we look at the 2s2p resonance in helium, and the idea is to measure the phase of the Fano profile. And these are the rabbit results. As you can see, with this technique, we obtain a very nice spectral resolution. We see very well the Fano resonance in the electron peaks corresponding to absorption of the 39th harmonic, and we see a nice phase variation in the sideband. I forgot to say that this is collaboration with the group of Pascal Salières. Okay, then we can look at and with the Fernando Martin and Luca Argenti. So now we can retrieve from these results the amplitude and phase, and you see a very nice interference structure, both for the amplitude and a nice high phase jump for the phase, and a good agreement between the experimental results represented in blue and theoretical calculation in red. And this is using the model from Fernando Martin and Luca Argenti. We can represent the Wigner distribution of this process, and which gives information about the temporal dynamics. And you can see in these results that we have a feature which represents direct photoionization in this process, and then we have a longer time scale which describes photoionization, and you see a strong interference. Now, the interesting part is when we looked not only at the sideband 38 that I showed you before, but also at the sideband 40. And in that case, as you can see here, you don't get as pronounced interference effect. The phase jump is not as sharp. There is a reduced contrast, reduced phase jump, obviously a loss of coherence. So how can we understand that? You can also see, obviously, on this, there is an echo. I don't know if you hear it. Okay, I continue, but there is so on this Wigner distribution, you also see obviously a loss of coherence between 38 and 40. So what is this due to? When you look at the atomic structure, you find that there is not only this 2s2p autoionizing resonance, but you also have a doubly excited state 2p2, which is very close to absorption of the photon here. And indeed, if you do a more complete atomic physics model of this process, you can reproduce this reduced coherence both for the amplitude and for the phase. So how can we interpret this? And again, this is an interpretation. Well, we are making a coherent superposition of a S wave packet and a D wave packet in this two-photon process, and the 2p square interact only with the S continuum because of selection rule. It does not interact with the D continuum. So we can write the wave packet that we create as the sum of this S contribution and D contribution, and we have a radial part and an angular part. Now, because if there is no 2p square and the two continua are flat, then the energy dependence of the two radial wave function is very similar, and you can factorize this out. You can say that the 2 degrees of freedom, the radial and the angular part, are separable. However, as is the case here, because of this 2p2 state, they are a bit different. That means that now we can say that this degree of freedoms are entangled. And since in this experiment, we are not doing any angular resolution, we angular integrate. Then we because of this entanglement, we lose coherence in the measurements. So this is how we interpret this this difference between the measurement on the sideband 38 and the measurement on the sideband 40. In the sideband 40, we lose a little bit the coherence of the wave packet due to this entanglement. So I would like to conclude by summarizing the results. I showed you how we can extend the rabbit technique to a multi-channel case and do really phase and amplitude retrieval of the different angular channels. To me, it's a relief, because during many years I thought that this rabbit is fine. It gives phase information, but this cannot only work in the case of one channel. I think here we showed that we could extend it to multiple channel, of course, assuming taking some information from this continuum transition. And finally, I showed you how we are going towards a higher resolution in our measurements, and how we start asking questions about the coherence of the electron wave packets, and going towards, okay, maybe we need to not only measure amplitude and phase, but even going towards matrix density measurements of the electron wave packet. I would like to thank you for your attention and acknowledge all of my colleagues, the groups working with the intense beamline. This is the groups working in this high resolution experiments, and of course collaborations with our theory friends, group of Eva Lindroth, Marcus Dahlström in Lund, and Luca Argenti and Fernando Martin. Thank you for your attention.
Thank you very much, Anne, for the very nice talk. We are a little bit late, so we have time for one question from the audience. I remind you that you have to post your question in the live Q&A, because I saw Alexander Kulev raised in the end in the attendees, but the way it works is that you have to post it in the live Q&A. So please post it there so I can read the question to Anne. Because at the moment I don't see questions, but I would ask one to you, Anne, referring to the first part, when you have been showing the nice experimental results from the two channels of neon and in a comparison with theory. I was just curious why in the experiment, I mean, this is probably maybe just noise. I mean, you showed also the error bars, but it seems that there's always a sort of oscillatory behavior on top, and it's not flat as in the theory. Is there a reason?
The last point is a little bit deviating from this curve, but the signal was very low.
Okay, because the sideband is very weak, and
yeah,
okay.
The sideband is very weak because it's the last harmonics. And I want to stress that these experiments were done with 10 Hertz systems. So yes. I think we can really improve the statistics. Of course, this 10 Hertz system produces a lot of photons. So, but still, I'm sure we can improve a lot the statistics in this type of measurements.
Okay, thank you. So I don't see other questions in the live Q&A. So I thank you very much, Anne, for the very nice presentation. And I remind all the attendees that they can discuss with you in the breakout rooms at the end of the session, all the details about your presentation. So meantime, I would invite then the next speaker, Pascal Salières, to join the stage. Okay, welcome, Pascal. So Pascal is now going to talk about imaging resonant photoemission dynamics in real time. I hear a little bit of background noise from your microphone, but I think it's fine. I mean,
Okay, so thank you, Francesca, for the introduction. My talk will be very much in the continuation of the nice talk of given by Anne, except that here we will try to address the question, how far can we go in the temporal reconstruction of the dynamics of photo emission, of course, in a more simple case, helium. So I will start by some reminders of the connection between the time and frequency pictures in photo emission, and then show you how we can resolve in time photoionization of helium, and then how we can do one step further and resolve both in time and space the resonant two-photon ionization of helium. So in a sense, it is shooting the movie of photo emission. I will first illustrate this time-frequency correspondence by using nice simulations performed by Basil Wurmser at LCPMR. So we will look at a wave packet that is centered at 54 eV that will scatter on this potential, and we will measure the electron flux going through our detector here, which is plotted here. So we will now look at the time picture, and what happens when the electron scatters, it is strongly modified and then it reshapes with delay with respect to the freely propagating electron wave packet, which is shown in dashed line. Actually, this delay is an advance, obviously because the electron wave packet has been accelerated in the potential, and so we find a scattering delay here of 60 or minus 60 attosecond. Now, if we look at the spectral domain, we can plot the wave function at the energy, at the central energy here, 54 eV. This wave function is strongly modified here in the potential, but asymptotically, we can see that it is shifted with respect to the freely oscillating wave function at this energy, and this is known as the scattering phase shift. Now, if we plot this scattering phase shift as a function of energy and take the derivative, we obtain a group delay, which is actually known as the Wigner delay. And this Wigner delay is indeed this minus 60 attosecond that we found in the time experiment, theoretical experiment. So you clearly see here the connection between the two domains, the two pictures, and we can use either to describe our process. So to access these scattering delays or ionization delays, we can either use the time picture and using a single attosecond pulse pump the ionization and then strike the electron wave packet with an infrared probe. This is the attosecond striking technique that was first used by Schultz to extract scattering delays. Or we can go to the spectral domain and then measure the spectral variation of the scattering phase using a broadband interferometric technique known as RABBIT, which uses an attosecond pulse train and a dressing field, as was done initially by Klunder with the first attempt by Essler. Okay, so Anne already nicely introduced the RABBIT technique, which I'm not going to detail again. What I would like to stress here is that this phase of the sideband gives direct access to the difference of the scattering phase of the two intermediate states. And then by dividing by 2 omega 0, that means their energy distance, we get an approximate of the Wigner delay. And I would like to stress that this is an approximate, because this may be problematic in some cases, for instance, when we have a resonance. Let's consider the autoionization of helium. At 60 eV, we can either ionize directly in the continuum or populate this doubly excited state, the 2s2p, that is coupled to the continuum by configuration interaction. And this leads to this well-known asymmetric Fano profile, and also to a very fast variation of the scattering phase around the resonance. So obviously, a single attosecond delay is not enough to describe the full dynamics here, and we need to measure the whole evolution of the scattering phase shift inside the resonance. So we can do this using the rabbit technique. If we use one harmonic that is resonant with this sp2 plus state, there are two ways to do that. Either we use a narrow bandwidth laser, and we measure a rabbit and then we scan the frequency. That was done by the group of Anne back in 2016. Or we use a broadband laser and a highly resolving electron spectrometer, and we can, in a single spectrogram, encode the whole information in the sideband, as we did in Clouson in 2016 also. So this is the result that we obtained. These are the amplitude and phase of the oscillating sideband that actually correspond to the autoionizing electron wave packet. And you can clearly see that we have very nice agreement with the theoretical predictions of Fernando Martin and Richard Talières. So now we have the amplitude and phase of the electron wave packet, and we can now go back to the time domain, we Fourier transform back, and we can reconstruct the temporal profile of the autoionization dynamics. Or we can also use a dual spectrotemporal representation where we can Fourier transform back to the to the spectral domain, but with a given accumulation time. So in a sense, we look at how the spectral profile of the resonance builds up in time. And this gives us this evolution. So you see, initially up to 3 femtoseconds, we have very symmetric spectral profile corresponding to the direct transition. And then later on, the resonance that has been populated and that has a lifetime of 17 femtoseconds starts to leak into the continuum and leads to interferences with the resonant path, constructive or destructive, shaping the Fano profile. Okay, so we have seen how we can indeed reconstruct the full temporal dynamics in this simple case. Let's consider another case where now we have 2-photon resonant ionization, but through bound states. So of course, the 1-photon transition does not lead to ionization for this path. Only 2-photon ionization is allowed for the 15+1 path. Actually, this was investigated by the group of Anne back in 2010 using harmonic 15 to excite the 1s3p resonance and then ionizing just above the continuum. And that's the reason why they could see variation of the phase shift only on one side of the resonance, and so a jump of pi½ was measured. So the question that we wanted to ask here is, first, are we able to reconstruct the full ionization dynamics in this case? That means we need to measure the entire phase jump around the resonance. And second, are we able to resolve this spatially, which means we need a high sensitivity and a high resolution, a spectral resolution. So to do this, we need to combine phase spectroscopy with momentum imaging. Actually, this was done in a very pioneering paper in the group of Mark Vracking in 2003, using a VMI in the context of the characterization of attosecond pulse trains. And this is only recently in the group of Ursula Keller that using a Coltrane's, these techniques were used to extract ionization, spatially resolved ionization delays. And then, as you see, there have been a number of other studies using both VMI and Coltrane's. In our specific case, what we want and what we need is, as I said, high spectral resolution and high angular sensitivity in order to be able to measure the phase at large angles where the signal, large angles from the polarization of the XUV and infrared laser, where the electron signal is very weak. So we built, actually this was the work of my previous PhD student, Dominique Platza. We designed a specific VMI spectrometer for high resolution studies with an original design of the electrostatic lens based on new metal electrodes, allowing a high capacity and a single microchannel plate detector to have a high resolution. And then we applied it to the case that I mentioned. We installed it on the Attolab beamline. So here is the general setup. We generate harmonics here in the gas cell, filter out the generating infrared, and refocus in magnetic bottle electron spectrometer here, combined with a fraction of the infrared, which is recombined here. And then we have a two foci geometry where we refocus the two infrared plus XUV radiation inside the VMIS and measure the angularly resolved rabbit spectrogram. The interest of having this intermediate angular integrated rabbit spectrogram here is that we can use a non-resonant gas, argon, for instance, and this provides a calibration for the XUV source. And so that this allows us to concatenate different measurements performed in different generating conditions so that we are able to shift the frequency of the laser by blue shifting the radiation in the gas cell. And so we can cover a 1 EV spectral range. So this is an image, a momentum map of sideband 16 that we get, and you can observe the two main contributions coming from the 1s3p plus infrared at very low kinetic energy, and the 1s4p plus infrared. So we are interested in this direct transition, this resonant transition M, and we are able to calibrate from the reference transition 17-1 to access only the two-photon resonant transition dipole moment. So this is the result that we obtain when we reconstruct the 0-degree amplitude and phase in the experiment as compared to the simulations performed by Richard Tayeb and Jérémy Kaya at LCPMR. So clearly we observe these two peaks corresponding to the 1s3p plus IR and 1s4p plus IR. In each resonance, we observe a smooth down shift of the phase that correspond to what was partially observed by Swoboda. But we also observe additional phase jumps in between resonances. You see this sudden phase jump here or here when we are between 4p and 5p. And these are really clear also in the experimental results, although they are slightly smoothed by the experimental parameters. So what is the origin of these phase jumps? To understand that, we can do a partial wave expansion of the two-photon transition in the S and D waves and look, for instance, at the S dipole matrix element. Again, amplitude and phase for the experiment and for the theory. We can write this dipole matrix element as a discrete sum over the resonant states that are involved, that are excited in our case. So actually, when we are on top of a resonance, for instance, on 1s3p, we are completely dominated by a single term where the omega, I mean the XUV frequency, is resonant with the 1s3p state. And then we have a boost of the amplitude, which appears here 1s3p and also 1s4p. And we have a corresponding smooth down phase jump due to the change of sign of this term around the resonance. Now, in between two resonances, now we have two contributions, each coming from the two neighboring resonances. And of course, I have opposite signs because we have one is above the resonance, so it's positive, and the other one is below the resonance, and it's negative. So the two at some energy position will compensate each other, and we have a change of sign, a sudden change of sign with a minimum here in the amplitude, which we also observe, also more noisy in the experiment. So that was for the S wave. Now, if we look at the D wave, we have exactly the same boost of the amplitude when we are near resonant, except that for the D wave, it's even stronger, and this is reminiscent of these Fano propensity rules. The main, so this is L independent in the resonant conditions, but in between resonances, now we highly depend on the value of this numerator here, which depends on L. And so it's not surprising that for the D wave, we have a different position of the cancellation of the two terms and the different position of this phase jump that we also clearly observe in experiments. Okay, so now we understand where these various spectral phase jumps originate from. And we can now look as a function of angle. So these are the different angles variations. So that makes a lot of information. But what we can already observe is that at specific position, we have strong angular phase jumps now. That means that given energies, for instance, inside each resonance, we have between the 0 degree and the 85 degree, we have close to pi phase jump. And this occurs also in between resonances. The origin of this appears clearly if we do a polar representation of the transition dipole moment. Here, if we focus, for instance, on the 4p resonance and do this polar representation where the r theta represents the modulus of the ionization amplitude, and the color maps the phase. And you see here the color map. And what we observe is that at high angles, we have a minimum and then a change of sign of the wave function or of the transition dipole, which gives this donut shape here at large angles. And actually, if we look at all the polar representations at the different energies, we have a wide variety of cases going through completely S wave to completely D waves that we clearly observe that are due to these cancellations that I mentioned before, where the S cancels, we have only a pure D wave, or when we D wave cancels, we have purely S wave. In the experiment, we have an excellent agreement for the high energy cases, as you can compare here, and slightly not so good agreement for the lowest energies, which is due to polluting low energy electrons in the spectrometer. Okay, so now we have the full information in the spectral domain on the transition. Can we now extract temporal information on this? We can do that simply by doing an inverse Fourier transform, and we can select a given zone of interest using this Gaussian gate. So first, let us look in the 1s4p region, which is shown with these rectangles, and make the Fourier transform for each angle. So these are the results. What is striking is first that we have very similar behavior, whatever the angle. And the second thing is that we have a maximum that is delayed with respect to non-resonant sidebands, which are plotted, which are centered at 0. And this delay maximum is, in fact, a measure of the transition delay through the resonance due to the transient trapping of the electron before completing the transition to the continuum. And this appears clearly if we plot the, sorry, we leave the pointer to show you the evolution in time of the polar representation, where you see that we keep the same shape. We have mainly an increase in amplitude and also a change of phase. You see here that we have blue and orange donut going to finally orange and blue donut. Very well. Now, if we look at the more pathological region in between resonances where we have all these strong phase jumps, what we get now is a completely different picture. As you see, we have a strong, at small angles, we have a strong destructive interference at 0, which is due to this strong pi spectral phase jump. And this destructive interference actually disappears at large angles. So the dynamics here is strongly shaped by the destructive quantum interferences at different angles. And here again, we can plot the evolution of the transition amplitude. And here you see close to 0, we have a strong destructive interference at small angles, so that we have an oblate distribution, and then we recover the initial shape, but again with a pi jump. So let me now conclude that we can combine rainbow rabbit interferometry with momentum imaging to perform a full characterization of the resonant 2-photon electron wave packet. And then we can reconstruct the attosecond photoemission dynamics. And we see that it is strongly impacted by these various pi phase jumps in both dimensions. And then, of course, this opens a number of opportunities by combining this with the techniques that Anne explained in the first talk, we'll be able to investigate very finely correlated electron dynamics as well as decoherence effects in photoionization. So let me now finish with acknowledgements to people who have done an excellent work in doing all these measurements and theory. First experiment, Alice Otiori and Dominique Platzer and Marius Lehmann at Lidl, and Basil Wurmser in the group of Jérémy Kaya and Richard Tailleb for the theory. Also Lionel Poisson at ISMO and the group of Frank Lépine and Vincent Loriot at ILM. And for the autoionization results, the group of Fernando Martin and Luca Argenti. Thank you for your attention.
Thank you very much, Pascal, for the very nice talk and also for being in time. So I don't see questions in the live Q&A. I encourage the audience to post some questions. Meantime, I could ask one question. So it's very impressive, I would say, both from your talk and Anne, it's clear that combining the usual rabbit with the angular resolution now, it's giving many more information, especially when we have these multiple channels contributing. I was wondering how critical is the inversion algorithm for the VMI images? So at the end, you extract right? I mean, you run inversion, you extract Legendre
yes,
coefficients that you have to, I mean, at the end, use for the whole interpretation. And you were mentioning that, for instance, you use a single plate MCP, maybe you have a noisy signal. So we're just wondering in terms of reconstruction, how critical this is, which kind of algorithm you use for the reconstruction.
Okay, for the reconstruction, we didn't use the p-Basex classical algorithm. We used rather the Davis algorithm, which worked really nice as soon as we have well centered the image, so we don't do any symmetrization in this case.
Okay.
We are able to extract directly the coefficients of the Legendre polynomial for each delay, and then we use an analytic formula to extract the phase at the various angles from the Legendre polynomial.
Okay,
and this is why we are able to also extract at very large angle. You have seen up to 85 degrees, where the electron signal is very, very weak.
No, exactly. I was wondering this because I saw these very large angles,
yes.
and I was wondering how critical is the inversion and
actually,
how well is reconstructing the signal that may be very weak, I guess, at this
Yes, yes. Actually, the largest angle are not the more critical ones. The more critical ones are, sorry, let me go back to here. The more critical angles actually are the ones where we have cancellation of the transition amplitude.
Because then you have no signal.
Yes, because there is basically no signal by definition there. And so this is where, for instance, we have this deviation. You see the 70 degrees in the experiment here, where we have this strong deviation from the expected theory curve. So this is an example of the distortion induced by this low signal-to-noise ratio at this specific position. But then at higher angles, we recover larger signals. So the extraction is still good.
Working even better. Okay, thank you very much. I have a comment from Mark Bracking in the Q&A. So it said, I don't really have a question, but a comment. We have recently done a very similar experiment under review, where we have obtained results very similar what you show. It has showing all the same phase jumps. Our experimental method has been the insertion of a narrowband interference filter in the IR beam used, and then angle tuning this filter in order to vary the central wavelength from about 770 to 805 nanometers. Accordingly, we have seen phase jumps associated with 4P, 6P, including the jumps in between the resonances. So that's the comment of Mark.
Yes, that was. This is what I mentioned here in this Drescher et al. Archive, where they indeed could measure this type of high spectral phase jumps, which were angularly integrated.
So either you use the rainbow or you tune carefully the.
Yes, actually, yes. Actually, here we have concatenated three measurements that are enough to cover these 800 milli-electron volts to get all these measurements. So it's quite, in principle, it's quite fast because we just need three spectrograms to get the whole information.
Okay. Thank you very much, Pascal. So again, you can discuss with him in the breakout rooms afterwards if you have other questions or comments. Thank you very much. So now I will call on the stage the next speaker.